Welcome to part 8 of the Yaesu FT101 restoration series, where I'm trying to restore a very early FT101, probably from 1971, and get it back on the air. Now, in the last video, we took this radio through the poor man's alignment, and it's ready to go on the air now. The finals are a little bit soft, and I don't quite have the right microphone for the radio, but it's working okay on the air on all bands. So I would say that all this radio needs to be used as a station is maybe a fresh set of finals. I want to go through the neutralization process next. A lot of fun because there's so many myths and so many pet methods of doing neutralization, and some of them are a little bit avant-garde. There are good, better, and terrible forms of neutralization. Some people are so afraid of neutralization, in fact, that they never would attempt it on their own. The threat of high voltage, the threat of doing something wrong where the thing oscillates and destroys itself. These are typically the people that keep one hand or both hands in back pockets when working around high voltage. When you're working around high voltage and you have both of your hands in the back pockets, that's even safer than having one hand in the back pocket. It's going to be a lot of fun. It'll just be dedicated to neutralization theory and neutralization styles, I'm going to call it. I would like to demonstrate neutralization on the Yaesu FT101 using two methods and some variations on those methods. When completed, I hope to show that dipping and loading the radio using the normal plate current meter method for rated output will provide the exact same output as tuning for maximum. The conditions will simply coincide. That's the final proof that you've actually neutralized your radio. Let's go to some neutralization history now. It's not new. In the very first edition of the Radio Amateur's Handbook in 1926, the crystal-controlled master oscillator power amplifier described the MOPA. It had a neutralization discussion as part of the article. And quoting that, there usually is some regeneration present in an amplifier all the time due to the tube's interelectrode capacities and the disposition of the coils in the circuit. They describe one negative effect if unchecked. If feedback reaches a large enough value, the crystal will become shattered in the oscillator. In neutralizing the power amplifier, start by turning on the filament supply for both the master oscillator and the power amplifier tubes. Connect the plate supply to the master oscillator but not to the power amplifier tube. Now adjust C4 until there's a minimum change in the deflection of the oscillator milliamps when the tuning condenser in the final, C1, in the amplifier is varied. This method with filament on and no plate voltage on the final would be described today as forward cold neutralization. Then they describe hooking up the B+ to the final. The issue here is that modern radios do not always give you a way to easily disconnect B+, turn filaments on and off in stages separately, inserting meters, but all manufacturers have to show some kind of procedure for neutralization in their manual. So here's a typical procedure for a Hallicrafter's radio from the 1960s. I'm not going to bore you by reading it, so you might check that out sometime. It doesn't really sound fun or effective, but it does recommend 15 meters as the band to do it on. Not 10 meters, which is the advice in the Yaesu manual. The procedure for the Yaesu FT101 is similarly a best-you-can-do procedure that accomplishes the task. You got to publish something, and they put this in the manual. Because the Yaesu write-up has all the stages active, high voltages on the final, heaters are lit, we call this type a forward hot procedure. I will attempt this procedure as written, and we're going to evaluate it. Why don't we have some basic neutralization theory before we get started? Why do we need to handle that feedback in the power amplifier? Well, basically because we don't want the stage to take off or oscillate. This could damage the tubes, produce spurious outputs, and at the very least it's going to steal power away from your output signal. So less power out too, guys. The standard amplifier is a phase inverter. We really shouldn't have any issue because the output signal is out of phase naturally from the input signal. But then we have these darn tuned circuits that we stick on the input and the output. The nature of a tuned circuit is that of an ideal phase shifter based on how you tune them. In fact, there's a 180-degree shift from the top of the tuned circuit to the bottom of the tuned circuit. So it's pretty easy to get positive feedback and start and maintain an oscillation. Such is the mechanism of the tune plate, tune grid power oscillator. A first principles way to counter positive feedback is to simply couple enough negative feedback between the tuned circuits to fight the effect. We call this loop neutralization. If set up correctly, this is guaranteed to work, at least over some minor bandwidth. But the preferred method is to counter the interelectrode capacitance of the tube with an exact opposite amount of negative feedback in order to cancel it in bridge fashion. In other words, we're canceling out the capacitance of the tube with an external capacitor that's in an opposite side of a bridge. There's two basic ways to accomplish this. One is called Hazeltine or plate neutralization, and the other is called Rice or grid neutralization. These systems both worked over a wide frequency range, so they're preferred. When beam power tetrodes like the 6L6, 807, 1625 variant, and so on came along, the feedback mechanism was reduced somewhat by the Faraday shielding effect of the screen grid. In many simple transmitters, this alone could reduce the need for neutralization. But in practice, you're still flirting with danger. You do need neutralization. The famous ARC-V command transmitters used grid neutralization for the pair of 1625 tetrodes, and one cap fit all the bands, basically from 2 to 9 megahertz. Notice how small in picofarad that this homemade feedback capacitor was that they put into these radios. This method was a bit crude at best, and it would be impractical to use for tetrodes like sweep tubes or 6146 tubes, because adjusting such a small capacitance becomes very difficult. A better way was required for single-ended neutralization of modern beam power tetrodes. This was known as the Brune method, developed by Warren Brune, W5 Ocean Lima Yankee, while at Collins Radio in 1950. It is basically a form of Rice, so this method also depends on a grid bridge circuit. The fact that any resonant circuit, the ends of the tank are 180 degrees out of phase at any moment, and that the grid circuit's always supposed to be resonant on the frequency of interest, this is the key to making the bridge work. The capacitor at the bottom of the tank provides two functions. First, it's required because you need an RF bypass for that tank. So that allows maximum power to be fed into the grid of the final. This is a very important capacitor. Secondly, it forms an uneven voltage divider, a divider between ground, that point where the bottom of the tank touches the top of the capacitor, for the neutralization point. So this capacitor would normally be something like a 1,000 picofarads, a 0.01 microfarad, which would provide a nice, stiff, low impedance bypass point. But by deliberately making it smaller, say 100 picofarads, 200 picofarads, 680 picofarads, something like that, for a 2 to 30 megahertz system, this lifts the tank off ground slightly on the bottom, allowing some out-of-phase RF neutralization voltage to be induced back into the tank. This has the effect of lifting the tank and canceling out the feedback. This is why the quality of that C11 cap, the 200 picofarad cap in the FT101, is very, very important. Again, please note that this circuit only works when the grid tank circuit is actually tuned correctly on frequency. This means that the neutralization can be made inoperative if the controls are not set correctly. If you don't peak the driver right, if you don't tune the output correctly, you could go into an unstable condition and the final could take off. Neutralization is not the panacea to all problems if you don't know how to tune your radio. Notice that the neutralizing capacitor is in series with a blocking capacitor, C125 in the ASU. The elaborate band switching of the FT101 is a bit hard to follow, but you can see that the critical cap we are working against is always C11. By the way, the Drake TR4s, the sweep tubes had fairly high interelectrode capacitances. The minute grid-to-plate capacitance with VHF tubes like the 6146 that have very low capacitance, They were getting away with a single wire poking up into the final cage, or a strip poking up into the final cage alongside the tube, and it became feasible to use something as simple as that in low-cost solutions. The DX60 and even the Collins KWM2 have an oversized strip that's located in between the two tubes, and it's further adjusted with a trimmer. I believe the Heath Apache uses this method as well. Manipulating the capacitance ratio between C125 and C11 can also permit a larger value of trimmer to be utilized, or a smaller value. The fixed blocking capacitor between the neutralization capacitor and the final plate circuit of the ASU provides two functions, as I mentioned. Most importantly, it allows the designer to optimize the tuning rate and range of the neutralization variable. Playing with this capacitor's value can allow this circuit to accept any brand of 6JS6 or 6146 types. And secondly, it provides some added high voltage protection to the grid circuit. As far as counting on it for protection against you or your body getting a shock, I don't really think so. Always use an insulated tool. We'll have a little more on this when I attempt to swap out the final circuit to 6146s in a later video. So let's try the forward hop method first, outlined in the FT101's manual. Oh, and why do we neutralize between 14 and 30 megahertz? Because that's where the typical sweep tubes and beam finals like 6DQ5, 6LB6s, 6JS6s, 6146s, 813s, and so on, it's where they take off. Similarly, the typical chokes we use get kind of squirrely around 20 megahertz. So Tom, W8JI, a very knowledgeable RF engineer, suggests that 15 meters is the ideal band to use when you're neutralizing your radio.
Okay, so here we are with the 101 on 15 meters. I've tuned it up on 21.2, and we are in the tune mode, and I'm just going to show you the output power. It's putting out about 50 watts when I dip the plate. Okay, I'm dipped. Okay. However, when I mistune, I can bring the power up to almost 100 watts. Matter of fact, when I optimize everything, I can easily get it over 100 watts. But that's nowhere near coinciding with the dip. Okay, there I've got a good dip, and it's around 60 watts, but when I play with the loading control, get it up to full power, I'm nowhere near the dip. Okay, that is a sign that we are not neutralized. And I haven't touched the neutralization cap on the transceiver, so we know we've got some work to do. So next I'm going to put the unit on its side, and we will consult with the final amplifier neutralization instructions right out of the manual. And we'll try to neutralize the transceiver using their method, and their method has everything on. And basically you have to have a tuning tool, and I suggest that before you try to turn that neutralization capacitor with a plastic tuning tool, that you first spray it with some lubricant like deoxit, and loosen it up with a regular screwdriver, power off of course, everything discharged, and get that neutralization capacitor ready to move, and you'll find it much easier with your tuning tool after you do that. So this is a little tricky, but at least you have a good view of the S meter, which is, we're going to be in the current position, okay, measuring IC, or the plate current of the final, and we're into a dummy load. We have our plastic tuning tool, and I have verified that it can turn the neutralization cap, which is in this hole with the big N on it. You guys have seen that hole before. Let me just swing this over so you can see it. See the N? That's where I'm going to be sticking the tool to get to the head of the neutralization cap. So it says here that we need to advance the carrier control until the meter reads 100 milliamps. So we're going to be tuning up the transceiver at 21.2 megahertz, not the 29 megahertz that they say in the procedure. And we're going to back off on the carrier control till we get 100 milliamps. So let's just back off on the loading a little bit. Let's dip the plate. That's good. And now let's back off till we have 100. Okay, close enough. And by the way, I'm looking at my power meter, and that's just about 10 watts out. Now that's not going to hurt the finals. We're just trying to protect the finals here. Rotate the plate tuning control, observe the dip, indicate on the meter. If the dip is not prominent, reduce the loading control, I already did, slightly for better indication. So let's just see if we get a dip. Oh yeah. They want you to look at that meter as you rotate through resonance. It should rise equally and smoothly on each side of the minimum dip indication. Now, we're not seeing that, are we? As we rotate that control, on this side it's real slow, but on the other side it comes up very quickly. Slow, quickly. You see that? That's an indication that we're not well neutralized. Determine which side of the dip rises abruptly and set the plate control slightly to that side, keeping the meter reading below 100 milliamps. Now, using a non-metallic tuning wand, rotate the neutralization capacitor shaft very slightly in the direction which reduces the current shown on the meter. Okay, let's try that. So first of all, we're going to go to that rapid side. Okay, definitely higher on that side. So I'm going to go on this side a little bit. Now I'm going to go in and find the neutralization cap. Okay, here we go. There it is. I reduced it a little bit. Okay, now we repeat the process. It's closer. See what I've done? Now it's dipping pretty equally on both sides. You would repeat that process several times until you get that dip as close to equal on both sides as possible, and that's their method. Big deal. So repeat steps 6 and 7 until the meter indicates a smooth and equal rise on either side of that minimum dip point. And they just have a note here: the final compartment cover must be in place to supply shielding required during the neutralization procedure. We're done. There it was. Hot neutralization accomplished in one adjustment of the neutralization control. That's the method that they put in the Yaesu for the FT101. We're on 15 meters, and remember, before we did the neutralization, the dip and the peak were way off as far as tuning the plate. So let's see if we get maximum power out at the same point where we have our dip and loading correct. Okay, we're over 100 watts, and we got quite a bit of plate current showing. But let's just see if the dip is there. Oh yeah, we've got excellent correlation. Excellent correlation now between the dip and maximum power out. Let's take the loading down. Should get a deeper dip. Again, power output and dip and load are coinciding. That's why I say it doesn't really matter which method you use on your transceiver, but your transceiver must be properly neutralized. So the second method that we're going to try for neutralization is the one that's suggested by Fox Tango, written by Peter Roberts, G4 Delta Juliet Bravo. He calls this cold neutralization. And by cold neutralization, he's actually removing the filament from the finals. So the transceiver is probably only doing leakage output, possibly a fraction of a watt at most that would leak through just from the driver. I'm looking into the transceiver right now to see if I can see the finals lit up. I can see that the final's lit up. So let's turn the rig off, pull that plug, and then turn the rig back on to see if that final's extinguished. Also, I want to note that this is also a forward method. And by a forward method, I mean from the VFO all the way out to the output. You're actually measuring power at the output of the transmitter. You're not putting power into the antenna terminal. You're putting a detector or some other method of measuring power at the output of the transmitter. We call that the forward method. Okay, I cannot see the finals lit up, but I do see the driver lit up. So pulling that plug, and this is the plug right down here. This is the plug we removed from the back. We've killed the heaters in the final. And this is a fully tuned up radio, by the way. I'm going to put it in the tune mode, put the meter in the sensitive mode, and hit transmit. Nothing. Not even registering on the meter. We have a T set up between the output of the transceiver and the dummy load. The T is connected to a simple detector, which consists of a 1N34 diode, or 1N270 probably, a 1K resistor, and a 0.01 microfarad capacitor. So the resistor is right across the output of the T. The diode goes to the hot on the meter. The capacitor goes from that point to ground. A simple crystal radio attached to the multimeter. So let me get the neutralization stick, the insulated tool, into the neutralization port. We have the plug out of the back of the transceiver, so the finals are not lit up. We have high voltage on the finals. The driver is lit up, and it has medium voltage on it, medium voltage. Something under a watt's going to come out of the transceiver, and this little detector should see it. Here we go. And that tone is coming out of my monitor receiver. 2 volts. Okay, now I'm going to turn the neutralization cap. That wasn't too bad. We're able to find a nice null using the simple detector. Okay, this is neutralization detector 2, and we're using the forward cold method. Okay, we're going to use the WJ8711's meter, which is calibrated in dB. I'm going to hit transmit and peak the controls. That's the driver. And that's the final. Now I'm going to get on the neutralization cap. Okay, I'm on the neutralization cap now. Okay, you can clearly see the null. I could probably use some more dB of attenuation in the form of pads between the T and the receiver. I suggest you use something like 50 dB of pads if you want to get the receiver, to show the null clearly. So please do use an attenuator, preferably 20 to 60 dB in front of the receiver. Okay, method 3, same thing, into a scope. Okay, same thing, we have the 20 dB pad going right into the scope. And again, this is just a straight T in series with the output of the transmitter into the dummy load. Here we go. That's all there is to it, folks. We have another problem. Do you remember when we did the neutralization using that T, we had the attenuator coming off? Well, now we didn't have a 50 ohm load anymore. We had a 25 ohm load. We're double terminating. So we were really going into a 25 ohm load instead of a 50 ohm load. Well, it really didn't influence much. It's still You know, it is a mismatch. You can do better. You can always do better. You could use, for instance, a 10-to-1 voltage divider there that would not disturb the 50 ohms. You could have, for instance, a series 1K and a 100 ohm to ground. And with that voltage divider off the 50 ohm load, you could send that into the scope or send that into the receiver. And you could add all the attenuators you want on the other side without disturbing the 50 ohms. So keep that in mind. You can always do a better job at this. But we've accomplished what we want to accomplish. The radio is properly neutralized now. You can do neutralization either going forward from the transmit section out the antenna, or you can do it in reverse by force feeding a signal into the output of the transceiver and sensing on the driver's plate. Okay, that's a reverse. Now, that's a little hard to accomplish with the FT101 because of the TR relay, but I'm actuating the TR relay with the power supply externally. Otherwise, the radio is completely dead, no power cord attached. This is a completely safe, cold reverse method.
I've got a wire wrapped around pin 7, which is the plate of the 12BY7. Let's see if we can use that as a tap point. Okay, seriously, what subscriber had this crazy idea?
So let's try the reverse method. I'm going into the output of the transceiver through a 10 dB pad. I have the receiver connected to pin 7 of the 12BY7 through a 10 picofarad capacitor and a 10x scope probe, just going into the receiver. Let's actuate the relay. Now let's maximize the driver and the output network. We're ready to rock the neutralization capacitor. Again, this is a completely cold method. Filaments are not on, high voltage is not on. The transceiver is dead except for the relay. I don't suggest this for transceivers because of the relay issue, the TR relay, but it works very well for simple transmitters like the DX60, DX40, the typical simple 6AG7, 807 type transmitters. A little bit trickier to do with the transceiver. So this video got a little bit long, but I think we covered most of the neutralization techniques that you might be interested in. Okay, we didn't do the crazy ones that Heathkit came up with the grid dip meter, but we covered quite a few. And now we're getting the effect that we want with the peaking and the coinciding with the plate current dip. So next week we're going to get into filters. We're going to explore the single sideband filter in the early FT101 and how we might even replace that with a better filter.